Have you ever wondered how stress distribution in dental implants is predicted? It's a fascinating blend of bioengineering, material science, and patient-specific factors. Dental implants are a common and successful treatment option for missing teeth. Made of a titanium alloy, they are surgically implanted into the jawbone to replace the root of a missing tooth. The implant then supports a crown, bridge, or denture, restoring function and aesthetics. The success of these implants is not just a matter of surgical precision, it's also about how well the implant can handle stress. Excessive stress on the implant can lead to failure. This stress arises from a variety of factors. These include the implant design, the properties of the material from which the implant is made, the daily activities that subject the implant to diverse loading conditions, and individual patient factors such as bone density and oral hygiene habits. Implant designs vary, and these variances significantly impact stress distribution. The dimensions of the thread, for instance, can influence how stress is distributed across the implant system components. The material properties of the implant also play a crucial role. Dental implants are typically made of a titanium alloy, a choice that balances strength, biocompatibility, and resilience. Loading conditions refer to the forces that the implants are subjected to during daily activities such as chewing and speaking. These forces can vary greatly, and the implant must be designed to withstand them without failure. Patient factors, on the other hand, are individual considerations that influence stress levels. For instance, a patient with low bone density may require a different implant design to ensure optimal stress distribution. Predicting stress distribution in dental implants is, therefore, a critical aspect of their design and engineering. It ensures the longevity and durability of the implants, contributing to the overall success of implant-based treatments. The anticipation of stress distribution is not just about avoiding implant failure, it's about enhancing resilience and crafting a proactive approach to dental health. Predicting stress distribution is crucial for the success of these implants. Let's explore how it's done. Why should we care about predicting stress distribution in dental implants? Well, the answer is simple yet significant. The process of predicting stress distribution plays a crucial role in the engineering and design of dental implants. You see, by accurately predicting stress, engineers can craft implants that demonstrate enhanced resilience. This is of utmost importance because it helps to minimize the risk of implant failure. And as we all know, the fewer the failures, the longer the life of the implant. But it's not just about longevity. Accurate stress prediction also contributes to the overall success of implant-based treatments. It ensures that each implant is designed with the utmost precision, catering to the unique needs of the patient. In essence, predicting stress distribution is a proactive measure. It's about foreseeing potential challenges and addressing them head-on, right from the design stage. The better we predict stress, the better we can design for success. How can we predict stress distribution in dental implants? This is a question that has been at the forefront of dental implantology research for quite some time now. The answer lies in the use of experimental methods that have been developed to predict stress distribution, such as strain gauges, photoelasticity, and X-ray diffraction. Strain gauges, for instance, are devices that measure the amount of strain, or deformation, in a material under stress. They are attached to the surface of the implant and record changes in resistance as the implant is subjected to stress, providing valuable data on stress distribution. Moving on to photoelasticity, a visual technique that uses polarized light to study stress distribution. A model of the implant and surrounding bone is made from a photoelastic material which changes color under stress. When polarized light is passed through the model, the areas of stress show up as bright bands of color, giving a clear picture of stress distribution. Then, there's the X-ray diffraction method. This technique involves shooting X-rays at the implant material, which then scatter off the atoms in the material. By studying the pattern of scattered X-rays, scientists can gain insights into the stress distribution within the material. However, it's important to note that while these methods have proven useful, they do have their limitations. Strain gauges, for example, only provide surface data and cannot measure stress distribution inside the implant. Photoelasticity, on the other hand, requires a clear model and cannot be used directly on patients. X-ray diffraction, while providing in-depth data, can be time-consuming and expensive. Despite these limitations, these methods have been instrumental in improving our understanding of stress distribution in dental implants. They have paved the way for the development of more advanced techniques, such as the finite element method, which we will delve into in the next part of this series. Despite their limitations, These methods have paved the way for more advanced stress prediction techniques like finite element method. So, what's this more advanced method for predicting stress distribution? Let's dive into the world of the finite element method, or as it's often abbreviated, FEM. It's a numerical technique used to solve complex mathematical problems, and in the context of dental implants, it's used to predict stress distribution with a high degree of precision. You see, in FEM, the complex structures of dental implants are broken down into smaller, simpler parts, often referred to as elements. Each of these elements shares nodes or points with the elements adjacent to it, forming a network or mesh. This meshing process allows us to transform a complex problem into a series of simpler ones that can be solved more easily. The beauty of FEM is that it can handle a wide range of geometries and material properties. Whether you're dealing with different shapes of dental implants or variations in the titanium alloy used, FEM can tackle it all. This flexibility is a major advantage over more traditional methods of stress distribution prediction, which may struggle with complex structures or varied materials. FEM also shines when it comes to the ability to simulate various loading conditions. Remember, dental implants are subjected to a whole host of forces during daily activities like chewing and speaking. FEM allows us to model these diverse loading conditions and see how they influence the stress distribution in the implant. So, how does FM compare to the other methods we've discussed? Well, while experimental methods like strain gauges and X-ray diffraction have their place, they can be expensive, time-consuming, and may not accurately capture the geometric complexities of dental implants. FEM, on the other hand, provides a more cost-effective, efficient, and accurate solution. FEM, with its precision and accuracy, has revolutionized the way we predict stress distribution in dental implants. It's a powerful tool in the hands of biomedical engineers, enabling them to design and optimize dental implants for better performance and longevity. As we continue to push the boundaries of technology, who knows what further advancements we'll see in this field. Let's dive deeper into the finite element method, FEM, and understand how it works. The first step in the FEM process is mesh creation. We break down the complex structure into smaller, simpler parts known as elements. Imagine a puzzle. Each piece is an element, and when put together, they form the whole picture, or in our case, the dental implant. Next, we apply boundary conditions. These are constraints or loadings that the structure will encounter in real life. For example, the forces exerted during chewing or speaking. These boundary conditions help us simulate real-life scenarios and predict how the implant will react under these conditions. Now, we move on to the weak formulation. This mathematical approach allows us to approximate solutions to our problem by minimizing the residual over the whole domain. Simply put, it helps us to estimate the solution more accurately. After this, we calculate the strain, which is a measure of deformation representing the displacement between particles in the material body. This is where it gets interesting. We then calculate the stress, which is the force per unit area within materials that arises from externally applied forces, uneven heating, or permanent deformation. This helps us understand how much force the implant can withstand before it deforms or breaks. Finally, we visualize the results. This allows us to see how the stress is distributed across the dental implant. We can see areas of high and low stress, which helps us identify potential points of failure and optimize the implant design. With these steps, FEM provides a comprehensive method for predicting stress distribution in dental implants. Now that we've understood the mechanics and equations behind FEM, let's see it in action in our next section with a fascinating case study. Let's see how FEM works in action. In a fascinating case study, the finite element method was utilized to predict stress distribution in dental implants. The focus of the study was to investigate the influence of thread geometries on von Mises stress patterns, a critical factor in the longevity and success of dental implants. The researchers meticulously assembled the components and defined the material properties with precision. They then proceeded to analyze two distinct dental thread geometries. The first model had a thread height of 0.5 mm, a thickness of 0.2 mm, and an angle of 30 degrees. The second model had different thread dimensions, allowing for a comparative analysis. The results were revealing. The static analysis showed that variations in thread height, thickness, and angle significantly influence stress distribution across the implant system components. The model with a thread height of 0.5 mm, a thickness of 0.2 mm, and an angle of 30 degrees demonstrated a more favorable stress distribution profile compared to the other one. This finding suggests that by making specific adjustments in thread dimensions, we can positively influence the load transfer dynamics within the implant-bone interface. In simpler terms, the right thread geometry can help distribute the stress more evenly, reducing the risk of implant failure. But what does this mean in practical terms? Well, it means that engineers and dental professionals can use these findings to design and manufacture dental implants with enhanced resilience. This not only minimizes the risk of failure, but also contributes to the overall success of implant-based treatments. This case study is a brilliant example of how the finite element method can be used to make significant strides in biomedical engineering. By leveraging FEM, we can predict stress distribution more accurately, inform design considerations, and advance the field of dental implantology. Through FEM, we can make strides in improving the design and longevity of dental implants. Using numerical methods such as the finite difference method, FDM, for predicting stress distribution in dental implants is crucial. This applies to a broad spectrum of stakeholders: researchers, engineers, dentists, and patients. Our investigations have brought to light that variations in implant parameters, thread height, thread angle, and thread thickness can significantly influence stress distribution and the transfer of load to the implant-bone interface. We discovered that enhancing the thread angle led to improved stress distribution within the model, leading us to some highly satisfactory outcomes. However, the journey of improvement doesn't end here. Future work could include the following steps. 1. Adding more parameters. Integrating additional parameters that may influence the outcomes into the system will significantly aid implant dentists. These parameters could range from corrosion resistance and osseointegration to characteristics. 2. Collaborating with dentists. Future work can also encompass more extensive collaboration with dentists specializing in dental implants. This would ensure that our decisions are tailored to their requirements and prioritize patient comfort. 3. Open source CAD parts. We encountered challenges due to the unavailability of free CAD parts. Therefore, making these parts freely accessible can significantly facilitate the process. 4. Additional simulation applications. The presence of more mathematical simulation programs will undoubtedly enhance results and comparisons between different models. While some are available, they are limited, not free, and require simplification for user-friendliness. Stay tuned as we delve deeper into the future of stress prediction in dental implants, exploring the potential advancements in biomedical engineering.